Welcome again to another exciting pre-calculus video. Today we're talking about zeros of polynomial functions. It is a review from what we did last year, so hopefully you remember it. Hopefully it is familiar to you. I do know that some of you have been talking about that, this particular theorem and the other things that we're going to be doing today as we've been working on finding zeros. So hopefully it will be a review. So here we go. We're going to be talking about the rational zero theorem. The rational zero theorem is a way to help us to figure out what possible numbers could be a zero of our particular function. So in order to find that, we're going to take the variable in front of the highest degree exponent, so the leading coefficient, and we're going to call that P, and then the constant is going to be called Q. So when I take the leading coefficient, I'm going to find all of the possible factors of that particular number. And then I'm going to find all of the factors of Q, which again is my constant. In order to find out what my numbers could possibly be for all of the numbers that could divide evenly, my rational zeros, I would be able to use any of those numbers with the constant divided by the leading coefficient and all those factors. That's kind of what this rational zero theorem says. So here we go. Here's a problem. I think it'll make it a little more clear here. So I want to list all the possible rational zeros. So the first thing I'm going to do is I'm going to figure out what my leading coefficient is and what my constant is. So my constant is 4, so that means all the possible numbers that I could have, the factors of 4, would be positive and negative 1, positive negative 2, and positive negative 4. Then I would list all of the factors of my leading coefficient. My leading coefficient is 1, so that makes it easy because I only have one term. So therefore, I would take all of the factors of 4 and divide them by all of the factors of 1. So that means I'm going to have 1 over 1, 2 over 1, and 4 over 1. And of course, both of those would be plus and minus. That's lovely. That's all the possible rational zeros, but unfortunately, it asks us to determine which, if any, are zeros. So then the next thing I'm going to do is I'm going to use either direct substitution or linear substitution or division, or actually I could also use long division if I wanted to, but I don't know if you want to. And I'm going to plug them into my equation. Remember, my equation was x cubed minus 3x squared minus 2x plus 4, and that's f of x. So when I plug those numbers in, I'm going to stick a 1 in for x, and I find out what I get, which is 0. I plug a 2 in for x. I plug positive 1, negative 1, positive 2, negative 2, positive 4, negative 4. In order for it to work, in other words, in order for it to be a 0, then that means our remainder has to be 0. So if I look here, and I've already done the work for you, the only one that has a remainder of 0 would be 1. So that means f of 1 is the only rational zero because my remainder is 0 because it divides evenly. And that tells me just that particular part. Of course, we're going to take that to the next step in a little bit. But right now, we're only figuring out which one divides evenly. And again, if you didn't want to use direct substitution, you could also use synthetic substitution or some other method to find out what you get. You probably don't want to get into the habit of using a calculator, though, because this part might not be on your non-calculator section of the quiz. Or it might be on the non-calculator section of the quiz. So here's another example. This one's going to be a little bit different because when I look at the 15, I have all the factors of 15, which are 1, 3, 5, and 15, positive, negative, of course. But now I have all the factors of 2 because that's my leading coefficient. So now I have positive and negative 1 and positive and negative 2. So when I do that with a coefficient that's a leading coefficient that's different than 1, it makes it just a little bit more interesting because now when I list all of my possible zeros, I could have all of the all of the numerator numbers, all divisible by 1, and then I would take all of the numerator numbers and also divide them by 2. So that's why now I'm going to have, instead of just 4 possible zeros, I could have 8 possible zeros. So it's going to make it a little more challenging when I'm going to try to divide. So there we go. The next thing we're going to do is we're going to substitute the values in. Now, I'm not going to show you how to substitute all of them because I think you can probably, hopefully, do that on your own. But if we do that, and substitute it back in, we'll find that -3 is a 0. And then you would have to go and find all of the other ones. When I get the -3 as a 0, I can also figure out that 5 and 1/2 are also zeros. Now, if you use synthetic substitution or synthetic division, you're going to get a depressed polynomial. So since my original equation was an x to the third, my depressed polynomial would be an x squared. So when I get an x squared, I would also get a polynomial that would be something that could be factored. So I could use it here, like I show you, and take, once I know that my x plus 3 is a factor, then I would be able to take the depressed polynomial and factor it to find my other zeros. I think in the long run, that's probably going to be better to use the depressed polynomial as opposed to trying to always just factor it each time or check all of the different solutions, because plugging it in 16 times is a little bit cumbersome. So there's my particular answer. In this case, I get -3, 5, and 1/2. And again, I could check it just by graphing the equation, which apparently I didn't show you. If I graph the equation, you could see that's where the zeros would occur at -3, 5, and +1/2. And of course, what fun would it be without a word problem? So there's my word problem, and I've got a water bucket. And I want to know, on what day will the water reach a height of 10 millimeters? So f of x represents the day when the water level reaches a particular height. So I'm going to use f of x equals 10. The problem when I do that is that I'm going to have to create a new equation. So once I have my equation as written there, I'm going to take it and substitute 10 in place of f of x, which would give me this equation here, x cubed plus 4x squared minus 2x plus 7 equals 10. Move the 3 to the other side. And then I have a new polynomial, which I'm going to have to solve, because remember, this is equal to 0. In order to solve it, I would be able to list, using the rational zero theorem, all of the possible solutions that I could get. Well, since I have a -3 here and I have a +1 here, luckily there's not going to be too many that I could choose because both 1 and 3 are prime. So I get positive and -1 and positive and -3. So lucky for us, I'm only going to get 4 solutions. But then you should start thinking about the situation here. We're talking about the number of days. So could I really have a negative number of days? Of course not. So instead, I'm only going to have 2 possible solutions that I need to check, 1 and 3. So I'm going to use synthetic substitution or synthetic division to figure out which one works. When I do that, I'm going to end up with plugging a 1 in, and lo and behold, my remainder is 0. Yay! So that means that 1 is a solution. So if 1 is a solution, that means day 1 is when the water reached 10 millimeters of height in my water bucket. Why I'd want to figure that out, I don't know, but I can if I wanted to. Moving on to the next thing. Upper and lower bounds test. The upper and lower bounds test helps us to figure out, when we're using synthetic substitution, synthetic division, what numbers would work as a possible solution. So I don't have to check all of my answers. So if I had 20 different solutions to check using synthetic substitution of possible answers using the rational zero test, I wouldn't have to do all 20 of them if I use the upper and lower bound. So when I have a negative number, so that's what that means, a negative number, and if I look at the answer, the bottom line, when I do synthetic division, if the numbers go every other one, positive, negative, then that means it is a lower bound. So that means I don't have to try any numbers that are smaller. So for instance, if I were to substitute in a -3 in my box, and I do synthetic substitution, and I end up with positive, negative, that means -3 is my lower bound. None of the numbers will go lower than that for my zeros. So I don't have to try if I had like a -5 or a -10. There'd be no reason, so I could save myself some time. So that's a lower bound when the signs go positive, negative, for however many are down at the bottom. If I have a positive number and I'm plugging it into the box, then that means that when every number in the bottom of the line is non-negative, otherwise known as positive, then that means it is an upper bound. So if I were to substitute a 3 into the equation and everything was positive, then 3 would be the highest possible number that I need to try. I won't need to try anymore. So again, it would limit the number of choices that I have to make. when I'm substituting and guessing and checking. So here's an equation. I want to find the interval in which all the zeros for that particular function must lie. So therefore, I'm going to try all of the different situations. So if I were to graph it, if I look here, I can see that my zeros are going to occur 1, 2, 3, 4, 5, 6 at roughly positive 6 and 2 and roughly negative 2. So therefore, I would know that I could say my interval could be between positive 7 and negative 3. So there's the interval that we're going to try, positive 7 and negative 3. So the first thing I'm going to do is I'm going to use my rational root theorem. My rational root theorem will tell me that, rational zero theorem, sorry, the other book calls it rational root theorem. Negative 12 would be our constant, and positive 1 would be my leading coefficient. So that means I could have positive and negative 1, positive, negative 2, 3, 4, 6, and 12. And I know that it's got to be somewhere on that interval. Now, I'm really not sure if it's going to be negative 2 and positive 6. I mean, it looks like it, but again, we're not necessarily going to have this on a particular quiz. It could be on the non-calculator section, so we need to know how to do it without a calculator. So I'm going to test bound limits. So if we think it's going to be at negative 3, I'm going to substitute in a negative 3. When I substitute in a negative 3, I'll notice that I have, and of course I'm using synthetic division, I notice I have positive, negative, positive, negative, positive. So that tells me that negative 3 is my lower bound. There's going to be nothing else lower than that. So I wouldn't need to check a negative 4. I wouldn't need to check a negative 6 or a negative 12 because none of those are going to work. So then I would think about my upper bound. Well, my upper bound, let's say 7. So if I try 7 and I substitute it in, notice that all of the signs down at the bottom here are all positive. So that means none of the numbers are going to actually work that are going to be bigger than 7. So there's no reason for me to test 12, well, positive 12. So now I can eliminate some of those answers to find out what the actual zeros are. And as I said, those are our possible solutions. We've already eliminated some of these because they're no longer going to be no longer going to work based on our upper bound and our lower bounds. We know we can only go between negative 1 and negative 2 and negative 3 and positive 1, 2, 3, 4, 5, and 6. The other ones have been eliminated because we have figured out what our upper bound and lower bound could be for our possible zeros. So if I were to check some of those, if I substitute a 6 in, I'm going to find that my remainder is 0. And again, I'm going to use the depressed polynomial. So I'm going to take these coefficients and use them down here so that I don't have to go back to the original. It saves me some time. Now I can see that this is going to be trying a negative 2 in there. If I substitute a negative 2 in there, again, I get a 0, and I end up with another term that factors. So now I have the term x minus 6 as one of my factors, and also x plus 2 as one of my factors. I'm also left down here at the bottom with a depressed polynomial, which is x squared plus 1. I know that I can't factor, and that's a plus 2. That doesn't really look like, it looks like a 12. Sorry about that. X squared plus 1 cannot factor. That's going to end up being a non-real answer. So if I were to actually have to factor this particular thing, it would factor into x minus 6, x plus 2, and x squared plus 1. And the only solutions that I would have on this particular graph of zeros would be positive 6 and negative 2. And that's kind of what that just says there. And like I said, we're not going to count x squared plus 1 because that would be imaginary. And we don't graph imaginary on this particular plane. Last thing for today, we're going to be talking about Descartes' rule of signs. And again, I think I heard people talking about this the other day. To figure out the number of zeros that are positive, or the number of possible zeros, I'm going to look at the sign and count the number of sign changes. So if I happen to notice that there were, say, 6 sign changes, there could be either 6 positive real solutions, or there could be 4, or there could be 2, or there could be 0. So I start with the number of sign changes, and then I have to go and subtract 2 each time, and those are all of the possible answers. because for some reason, this is the way Descartes created it, so that it would decrease by a power of, not power of 2, but a integer of 2 each time. In order to find out what my negative real zeros are, I would substitute a negative x in place of x and simplify the problem out. Once I've simplified the problem out, then again, I'm going to find the number of sign changes. The number of sign changes, again, would be some number and then a multiple of that down by 2. So here's an example of Descartes' rule of sign. Here are my original problems. And I can see that as I go from here to x to the 4th to x to the 3rd, that is a sign change because it's positive to negative. And then if I go x to the 3rd to x squared, it still stays negative, so it's not a sign change. And then if I go from negative x squared to positive 2x, that's a sign change. And then from positive 2x to 7, it's not a sign change. So that means there are 2 sign changes. If there are 2 sign changes, that means that there are either 2 or 0 positive real solutions. Then I need to figure out the number of negative real solutions. So therefore, every time I see an x, I'm going to replace it with a negative x. So instead of x to the 4th, I'm going to have negative x to the 4th. Instead of x to the 3rd, I'm going to have negative x to the 3rd, so on and so forth. And then obviously I would simplify. So a positive power, a negative number to a positive even power is going to be positive. A negative number to a odd power is going to change the sign. The x squared stays the same, the 2x changes, and the 7 just stays the same. So now again, I'm going to find my sign changes. I have positive to positive, which is no sign change. Positive to negative, which is a sign change. Negative to negative, which is not. And negative to positive, which it is. So again, now I have 2 sign changes again. So if I have 2 sign changes, that means I have either 2 or 0. And if I look at the next slide, that's exactly what it says. So Descartes' rule of sign tells us I have either 2 or 0 positive real zeros and either 2 or 0 negative real zeros. I wouldn't know exactly what those will be unless I actually go ahead and test it, which we'll talk about a little bit more in the next one. One last thing though for today, and I know it's long, but deal. The fundamental theorem of algebra basically says that you're going to have as many solutions as the highest degree. So if the degree is 4, you'll end up with 4 solutions. They don't all have to be real, but they need to be 4 solutions. If the degree is 10, then there should be 10 solutions or 10 zeros. So we'll talk a little bit more in the next one, the next video, about how to find more of those solutions. And if I tell you the solutions, what will the equation be? So that's something you can look forward to. For now, we'll just work on this the next time I see you. Bye.